In this video, we're going to work through 3 past VCAR questions, focusing on least squares regression equations and the applications of them. So in this first question from the 2019 Further Maths Exam 2, we have a scatter plot below showing the atmospheric pressure in hectopascals at 3 p.m. plotted against the atmospheric pressure in hectopascals at 9 a.m. for 23 days in November 2017 at a particular weather station. So here we've got our scatter plot, and good thing to take note of here is that we are given by the way that the scatter plot is presented what our explanatory variable is, so that's the 9 a.m. pressure, and our response variable is the 3 p.m. pressure. So our first question, a least squares regression line has been fitted to the scatter plot as shown. The equation of this line is given as pressure at 3 p.m. equals 111.4 plus 0.8849 times pressure at 9 a.m. Part A, interpret the slope of the least squares regression line in terms of the atmospheric pressure at this weather station at 9 a.m. and 3 p.m. So remember, when you see the words interpret, you are writing a comment and you're looking at the templates that you have in your bound reference notes. So we're interpreting the slope, and that is 0.8894. So here we're putting our sentence in. On average, the atmospheric pressure at 3 p.m. increases by 0.8894 hectopascals for every additional 1 hectopascal of pressure at 9 a.m. Looking now at part B. So use the equation of the least squares line to predict the atmospheric pressure at 3 p.m. when the atmospheric pressure at 9 a.m. is 1025. So here we're using the line to make a prediction, substituting in the 9 a.m. or the explanatory variable being 1025. And then we want to round our answer to the nearest whole number. So firstly, making our prediction, so our 3 p.m. pressure, just using our equation that we've been given, so 111.4 plus 0.8894 times 1025 gives us 1023.035, and therefore rounding our answer to to the nearest whole number, 1023 hectopascals. Part C now asks us if our prediction that we made in part B is an example of extrapolation or interpolation. And so in order to make our judgment there, we need to refer back to the original data. So easiest way is to go back to the scatter plot, and we're checking, because we substituted in the value for the EV, the 9 a.m. pressure of 1025. So we're looking for 1025 on our x-axis or on our explanatory variable axis, and checking that that value is within our data range, and it is. Okay, so that means that it is an interpolation because it's inside the given data range. Remember, when we're substituting in the EV, in this case, anything above our highest point working left to right or below our lowest point working left to right would be an extrapolation. Anything inside those two boundaries, so between 1013 and approximately just over that 1027 would be an interpolation. Part D, determine the residual when the atmospheric pressure at 9 a.m. is 1013, and round our answer to the nearest whole number. So in here, it's really important not to round our answer until the very final step. So here, when we want to determine the residual, we're going to calculate something. Remember, when you are looking at residuals, you need to know what is the actual RV or Y value and a predicted RV or Y value. So we have been given a point of reference on our EV, the 9 a.m, being 1013. So firstly, let's find our predicted 3 p.m. value. And we're just going to use, again, the regression equation that we were given on the previous page. So popping that in and substituting in 1013. And so that allows us to get a predicted value of 1012.3622. And we'll leave that as the answer at the moment. The second piece that we need is the actual 3 p.m, the actual value for when the 9 a.m. pressure is 1013. And so to get that, we need to refer back to the graph, because in this case, we're not given that information as part of the question. So if you don't see it as part of the question, that means you must be provided the information as part of the data. And so coming back here to our scatter plot, if we just get rid of our previous highlights, make it a bit easier to see. Remember, we're looking for an actual value when we had a an explanatory variable of 1013. So if we look at our graph, we can see we've got an actual data point here, and that has been plotted in line with a 3 p.m. value of 1015. So that means the actual value there is 1015. Now remember, your residual value is the vertical distance from this point to the prediction made by the line. And so we can see that it is more than 2 units, approximately 3 units, but because we have the equation, we want to find the exact distance according to the variables and the equation that we have, and then round our answer rather than making an estimate. So coming back now, we can say our actual value, 1015, and then putting that together to find the residual. Our actual value minus our prediction gives us a residual value of 2.6378, which rounds to a value of 3 as our answer. Part E. So the mean and standard deviation of the pressure 9 a.m. and pressure 3 p.m. for these 23 days is shown in the table below. Use the equation of the least squares regression line, so a big hint here, and the information in the table to show that the correlation coefficient for this data, rounded to 3 decimal places, is R equals 0.966. So least squares regression line and values of mean and standard deviation, and also a reference to an R value. That should point you to the way that we calculate the regression equation when we're given summary statistics. So key thing to remember here is that we have one equation, which is our y-intercept, and we have another equation, which is our gradient. And so in this case, we're going to use our equation for the gradient because it contains the standard deviations and the R value, the correlation coefficient. Now we already know the gradient from the equation we've been provided. So we know that our gradient, or the value of B, is 0.8894. So we can use that information and put it all together into an equation. Important to know or remember that when it is a show that question, we have to pretend we don't know what the value of R is. So what equation would you set up with the information we do have in order to find R if we didn't know what it was? So we would use that equation for B. Our gradient, we know, is 0.8894. That is equal to R times standard deviation of Y. Remember, Y is our RV, X is our EV. So standard deviation of Y, we've got 4.1884 divided by standard deviation of X, so 4.5477. Now, when we start to undo that equation and solve, we will end up with R equals 0.965697. When we round that value to 3 decimal places, we get 966 as required. So it's really important that you are able to recognise when we're presenting particular pieces of information, what formulas, what rules can you use to help you gain an answer that's required. Final part of our question here. What percentage of the variation in pressure at 3 p.m. is explained by the variation in pressure 9 a.m.? Round your answer to 1 decimal place. Now, hopefully, this sentence structure, percentage of the variation, is explained by the variation. Hopefully, those words sound a little bit familiar. They form the template for our R squared comment. So our comment or our interpretation of our coefficient of determination. So we need to find R squared. We can do that because directly above we've been told that R is equal to 0.966. And we can use that rounded version because it has been given to us as part of the information in the question. So our R squared is 0.966 squared. And when we do that, we get 0.933156. But I need to give this as a percentage. So that means I need to multiply by 100. So 93.3156. And finally, give my answer to 1 decimal place. So 93.3%. Moving on to our next question. So this one is from the 2017 Further Maths Exam 2, question 3. The number of male moths caught in a trap set in a forest and the egg density, or the eggs per square metre, in the forest are shown in the table below. Determine the equation of the least squares regression line that can be used to predict egg density in the forest from the number of male moths caught in the trap. We want to write the values of the intercept and the slope in the boxes below, rounding our answers to 1 decimal place. So firstly, we need to identify the explanatory variable and the response variable. But before we have to think too much, there's 2 giveaways, or actually 3 giveaways on this page. Firstly, we've got the way that the information is structured in our question A. We're predicting egg density from the number of male moths. So that should tell us that egg density is our response. The second place where we can see that is in the format that they've given us to complete the regression equation. So they have written our little template out. And remember, it is RV equals our intercept plus slope times EV. Finally, as we keep moving down the page, we can see they've actually given us a copy of the scatter plot. And so again, we should know our response variable is on the vertical or y-axis, and our explanatory variable is on the horizontal or the x-axis. But let's go back to our data. And so in order to get our regression equation, we're going to enter that data into our calculator. Remembering we have our EV and our RV. And so I've got my data entered in the calculator, and you'll notice there that I have just used the EV and the RV as my variable names, but you can call them egg density, moths, whatever it is that's going to help you remember which one is the EV and the RV. So now we're going to go into our menu, statistics, stack calculations, and then number 4, linear regression. My X list is my EV, my Y list is my RV. And there I have my value for the y-intercept at negative 46.8 and my value for the slope at 18.9. Okay, part B. So the number of female moths, so please note this is now a different scenario. The number of female moths caught in a trap set in the forest and the egg density in the forest can also be examined. And we have our scatter plot here below. Continuing over the page, the equation of the least squares line is egg density equals 191 plus 31.3 times the number of female moths. Draw the graph of the least squares line on the scatter plot on page 6. Now, in order to draw that least squares line onto the scatter plot, we need 2 key points of information. So let's go back to our scatter plot and we'll do a bit of working on the side. When I check my scatter plot here, I can see that my x-axis or my EV does not go back to 0. So I cannot actually use the y-intercept of that equation to help me plot the line. So remembering that my equation of my egg density for this one is 191 plus 31.3 times the female moths. So in this case, I need to calculate 2 coordinates. I can choose any value from low down on my x-axis, any EV value to substitute in, and any value further up towards the max values on the x-axis. So I'm going to, for my first point, I'm going to use that the female moth numbers is equal to 20. For my second point, I'm going to use the female moth numbers is 50. And so what I'm doing here is finding the egg density at both of those female numbers, so substituting in for my EV, and same again when I use the number 50. What that will give me are 2 points that I can plot, or 2 sets of coordinates that I can plot onto my graph, because remember, 2 pieces of information will allow me to draw a straight line. Okay, so grab your calculator, find those 2 sets of values, and we can see when there are 20 eggs, we have 20 female moths, we have 817 eggs. So 20 and then at just above 800, and 50, and we're coming up to 1,756, so approximately there. And then grabbing a ruler or something straight and drawing our line through our 2 points. Now we want to aim to draw or extend our line just past the known data. We don't have to go all the way to each end of the grid, but you shouldn't stop short. You should make sure you at least cover the data that you have represented on your scatter plot. So back to the rest of our questions. Part 2, we're being asked to interpret the slope of the regression line in terms of the variables egg density and number of female moths. So here we're interpreting our slope of 31.3. And so on average, the egg density increases by 31.3 for every additional female moth caught in the trap. Part 2. The egg density is 1,500 when the number of female moths caught is 55. Determine the residual value if the least squares line is used to predict egg density for this number of female moths. So again, with our residual, we need to remember our residual value is the actual, in this case, the RV egg density, minus a predicted egg density. So we have the actual value here at 1,500. And so we need to make a predicted value for this point of reference of 55 female moths. So firstly, our predicted egg density, using our equation 191 plus 31.3 times 55, gives us 1,912.5, and then our residual value, 1,500 minus our predicted, gives us negative 412.5. So remember, a negative residual value tells you that the actual data point was below the predicted. Part 4, the correlation coefficient is R equals 0.862. Determine the percentage of variation in egg density in the forest explained by the variation in the number of female moths caught in the trap. So again, hopefully we're recognizing the format of that comment leads us to finding our R squared value. So we want to find that as a percentage and round our answer to 1 decimal place. So firstly, we're going to square our R value, so 0.862 squared, and we get 0.743044. Make that a percentage, so times by 100. And then finally, give our answer to 1 decimal place as required, so 74.3%. Our third and final question here is from the 2019 Further Maths Exam 2 Northern Hemisphere papers. So question 4, we have the scatter plot below plots the variable lifespan in years against the variable sleep time in hours for a sample of 19 mammals. And so here's our scatter plot. On the assumption that this association between sleep time and lifespan is linear, a least squares line is fitted to the data with sleep as the explanatory variable. The equation of the least squares line is lifespan equals 42.1 minus 1.9 times sleep time, and the coefficient of determination is 0.416. So some things to note to keep straight. Our sleep time is the explanatory variable, which we can see in a couple of places. And our coefficient of determination, remember that is our R squared value. We are also seeing from the scatter plot a quick assessment that we are seeing a negative relationship. So that's worth keeping in mind when we have to start describing what we're seeing. We can also note that from this slope being a negative number there. Okay, so firstly, we want to draw the graph of the least squares line on the scatter plot above. In this particular example, on our scatter plot, we do have the ability to draw in our y-intercept. because my scale here on my EV, my x-axis, goes back to 0. So my first point that I plot can be, so if I plot my first point, that can be my y-intercept value. So when x is 0, my y-intercept 42.1. And so I can plot that point at 42.1, being as accurate as you can. My second point, however, I will need to calculate using the equation. So again, I want to pick something from the top end or the maximum sort of end of my EV, my x-axis. So I'm going to use the number 14. So when sleep is 14. So that means my lifespan is equal to 42.1 minus 1.90 times 14. And so that will give me the value that I can work with of 15.5. So my coordinate that I'm going to plot is 14 and 15.5. So 14, 15.5 in here. Again, I want to grab a ruler, draw a straight line through those 2 points as accurately as I can, and there's my regression line. Part B, we want to describe the linear association between lifespan and sleep time in terms of strength and direction. So only strength and direction. Now at the moment we know the direction is negative, but we aren't sure of the strength. Remember, it could be described as weak, moderate, or strong, depending on our R value. So firstly, let's check our R value using R squared. So our R value is going to be the square root of the R squared value that we've been given, the coefficient of determination. We also already know that will be a negative value. And so when I put that in my calculator, I end up with negative 0.64498. And so that indicates that I have a moderate relationship or association. So our strength, moderate, and our direction, negative. Be really careful with a question like this that you don't go on to describe form and outliers when they're not asked for. You only want to give exactly what they're asking for, because if you accidentally make an error, you can actually lose any correct marks that you have already gained. So just state what they're asking for. Part C, interpret the slope of the least squares line in terms of lifespan and sleep time. So here, interpreting the slope, we're talking about, on average, lifespan decreases by 1.9 years for every additional hour of sleep. So note, because we have a negative slope, a negative gradient, that we're decreasing by that value of the gradient. Part D, we're asked to interpret the coefficient of determination in terms of lifespan and sleep time. So we're commenting on our R squared value. And so the coefficient of determination tells us that 41.6%, so just changing that R squared value to a percentage, of the variation in lifespan is explained by the variation in sleep time. Really important that you use all of those keywords. The variation in is explained by the variation in, and getting those values in the right spot. Part E, the lifespan of a mammal with a sleep time of 12 hours is 39.2 years. Show that when the least squares line is used to predict the lifespan of this mammal, the residual is 19.9 years. So remember, show that question means you have to do all the calculations and work as if you do not know the answer. So we need to find the residual. When we want the residual, we need a point of reference, which is our 12 hours. and an actual value of 39.2 years. So we can use that now with our regression equation to find a predicted lifespan and then find our residual value by doing our actual minus predicted. So our predicted lifespan will be 42.1 minus 1.90 times our reference point, 12 hours. That gives us 19.3 as the life expectancy. And then our residual value will be our actual 39.2 years minus our predicted 19.3, and that gives us 19.9 as required in the question. That brings us to the end of this worksheet. Hopefully that was helpful, but make sure you do go back and annotate any additional notes for yourself. So when you come across questions like this in the future, you've got a strategy to have a go.